Hi everyone, and so hi everyone. I'd like to apologize for this little false start here. So now everything should be in order. Um, okay, and yeah, so obviously we're now almost 12 minutes late. So basically all the everything is going to be shifted down by 12 minutes. So all the speakers are going to have the same time as planned. Okay, so now I'd like to introduce this for the first speaker of our session. It's going to be Vikesh Siddhu, and he's going to talk about some recent advances in the quantum Shannon theory and additivity questions related to that. His talk is going to be entitled "Leaking Information to Gain Entanglement via Log-Singularities." So, I'll give you the floor.
Uh, Thank you, Frederick, for that introduction. And I thank the organizers for taking the time to put this mammoth conference together. Um, I'm Vikesh, and I'm currently at Gila CU Boulder, and I used to be at Carnegie Mellon at the time of this submission. I want to talk to you about essentially about how well you can preserve entanglement, and preserving entanglement from noise is sort of a fundamental question and related to a variety of things, including quantum information and error correction. Um, and essentially, the ideas being discussed here today are when it's a sort of one can somehow leak or allow a noisy channel to leak additional information to its environment. Um, and by allowing such leaks, we find that an increase in the ability to sort of preserve entanglement using the channel. And one of the tools used in our finding is these logarithmic singularities. And I will touch upon all these constructions. But before I go towards that, it's sort of important to clear out why care about any of this. Well, one of the reasons is that, well, entanglement has emerged as a fundamental non-classical phenomena over the past few decades. And not only would we like to understand this phenomena better, we would like to harness it in experiments and make our experiments more precise and useful. But also perhaps use entanglement in real-world applications. Any use in experiments in real world applications comes with using physical devices that are noisy. And as a result, there is strong theoretical interest and also practical need for protecting entanglement from noise. In particular, um, sort of one would like to know when, at what rate, and by what means can noisy entanglement be distilled back to pure form. And in trying to answer this fundamental question, one uses a variety of tools which are now in variety of fields. And these fields are labeled as quantum Shannon theory, quantum error correction, and optimization, all trying to answer questions of this type. Consequently, a study of these kinds of questions makes it sort of fertile ground for exchange of research ideas between all these fields. And um, what essentially we found by thinking about these things is that there are certain new ideas that help find state-of-the-art rates for protecting entanglement from noise. The first idea is this theoretical tool, which gives sort of a mathematical mechanism. And essentially, there are singularities in the von Neumann entropy, which can be seen to give rise to positivity and non-additivity in rates for protecting entanglement. And there is sort of a conceptual surprise, which is that allowing a noisy channel to leak information to its environment can boost its ability to protect entanglement. And in order to discuss this protection of entanglement that I've been referring to, let us try and quantify it. One way of quantifying the protection of entanglement is as follows. Think of any pure state psi Ra shared between an inaccessible reference R and another system A that you control. But you must encode this system in very many noisy systems that you actually have access to, and then decode it back. And suppose the encoding decoding can be arranged in such a way that, n times s number of qubits of the A system can be recovered with vanishing errors n tends to infinity, then one says that S is an achievable rate for protecting entanglement. Of course, this rate S not only depends on the channel, but also depends on the encoding and decoding. Doesn't depend on the state because it must work for any state. You can remove that dependence on the encoding and decoding and say that give me the maximum possible rate of this type, and this will define for you the capacity of this channel B for protecting entanglement. This capacity is a somewhat fundamental quantity and is connected to a variety of other quantities. And in particular, it gives you rate for preserving entanglement, but also you can think about it as a rate for distilling EPR pairs. And here's the essential connection. Well, you can protect any state. Why don't you try and protect EPR states? And while you're at it, view the output of the channel as if it was with a different party, and view the reference state as if it was kept with you, but you didn't do anything with it. In this way, you will be trying to preserve EPR pairs. And suppose you can preserve n S EPR pairs of high quality, then as n tends to infinity, then you essentially have a protocol for what is called distillation of EPR pairs. Okay, what can you do with these EPR pairs? Well, somewhat early insight is that EPR pairs can be sacrificed to send noiseless quantum states along with some amount of use of classical information. However, we don't really care about forward classical communication. It doesn't really increase rates for preserving entanglement. Um, and as a result, this quantum capacity is also a fundamental rate via this connection to sending quantum information from the input to the output of a channel. Um, and in addition, when people talk about sending quantum information in a noiseless way using a noisy system, one has to perform error correction. And so the encoding, decoding operations from the previous slide just become error correcting encoding and decoding operations. And as a consequence, the quantum capacity is a fundamental rate for doing quantum error correction. In fact, it is the ultimate rate for doing such tasks and the ultimate rates for all the other tasks that I just discussed. In addition to that, if you can share EPR pairs, then you can sacrifice those EPR pairs for communicating classical information in such a way that someone else listening to you doing this is unable to find out what information you communicate. Consequently, the quantum capacity gives you an achievable lower bound on quantum key distribution. So really, this is sort of one of the most interesting quantities to look at. It's connected to a variety of ways, and there's more than one way to introduce this quantity. I've today chosen the route of preserving entanglement. One could have chosen a different route and made those connections. And given this fundamental nature, one would like to first compute what are these achievable rates and then compute the best possible achievable rate, which is the capacity. There is a Shannon-like recipe for doing this, which has been developed over the years of study of this quantity. First, let me introduce to you the original Shannon recipe, which concerns classical channels sending classical information. Here, the channel sends an alphabet X an input X from an alphabet X to an output Y in an alphabet Y with probability P of Y given X. One would like to know how much classical information can be sent using arbitrary many uses of this channel. The idea is that you can express an achievable rate for doing that sort of task using the following recipe. The first ingredient is the Shannon entropy, which is of a probability distribution at the input, here written Hx, is just summation px log px with the minus sign. The second ingredient is the mutual information between the output y and the input x of the channel, and it can be written in terms of the Shannon entropies to the right side of the equality. Upon maximizing this mutual information over all input distributions, you obtain a number, here called the channel mutual information and labeled as C1 of n. This number is an achievable rate. Essentially, the same recipe can be replicated in the quantum case. Of course, you have to be careful about the quantities that you use. Instead of using the Shannon entropy, you use the von Neumann entropy, trace of rho a log rho a. Instead of the mutual information, you use the current information, which is the difference between the output and the environment entropies of a channel. And you maximize this to obtain the channel current information, Q1. And this gives you an achievable rate for sending quantum information or preserving entanglement, however you want to discuss this quantity. Uh, Next is a recipe for finding the channel capacity. Let's look at a classical channel first. Well, what happens in this case is that you concentrate on this achievable rate that we found, the channel mutual information, and you find it to be additive in the following sense. The for joint uses of a channel n and n prime, the C1 rate is simply the sum of the C1s of the individual channels. This allows you to write down the capacity in an extremely simple form. The capacity can be expressed as a limit of the channel mutual information over k uses divided by k when k tends to infinity. However, additivity ensures that you just get a single number, which is just C1 of n, and this limit simplifies. When you're using two channels and you want to compute their capacity, you again go back to the additivity on the first line and you get the capacity of two channels n and n prime used together. It's just the sum of the capacities of the individual channels. I mean, this is somewhat intuitive result, right? I mean, I'm trying to communicate with you using Zoom, and suppose I also try to communicate with you using Slack. Total amount of information at maximum I can send is the maximum I can send through Slack and Zoom separately. Next is the idea on how to generalize this to the quantum world. Lots of effort has gone into doing this, as into the previous slide, coming up with the results on the previous slide, none of which was by me. This is just known stuff. Essentially, the current information of can be non-additive in the sense that two channels B and B prime used together can have a current information of the joint channel, which could exceed the current informations of the sum of the current informations of the individual channels. Consequently, the capacity, again, written as a similar limit as on the second line under the first heading of classical channels, can exceed the current information of a single channel. And it is then possible, at least, that the quantum capacity of two channels B and B prime used together could possibly be larger than the capacity, sum of the capacities of the individual channels. Actually, all of those things occur. Non-additivity introduces challenges in the following sense: that the quantum capacity must be written as this limit. In fact, there are somewhat easy questions that are, or well, there are somewhat straightforward questions that are not easy to answer. One of the straightforward questions is, I give you a channel, can you tell me whether its quantum capacity is positive? Well, not using the route that I just discussed, because along this route, you must compute the current information for n parallel uses, and there are constructions by a wide variety of authors, Qubit and collaborators, and Elkaus and Streldruck, which say that, well, you can find a channel for which n uses of the channel is going to give you zero current information, but for some n plus one, it's going to give you a positive current information. This sort of drives the belief that even checking the quantum capacity could be extremely hard. But suppose you can perform this check and certify that the channel has zero capacity, then is the channel useless? Not really. You can have two channels B and B prime used together. The joint channel has capacity, individual ones don't. And this leads you to the question, when and why do these non-additivities occur? And in answering these questions, we have opportunities. You can develop new theoretical tools to understand this kind of quantum communication, hopefully gain some conceptual insight along the way, and perhaps, possibly as a goal, leverage the non-additivities that you find and trace them back to the quantum error correction insight that we discussed earlier, and see if you can leverage these non-additivities in some way. What I am going to present today is a tool to sort of understand the coherent information and these non-additivities. The tool is what I call logarithmic singularities in the von Neumann entropy. Essentially, if you have a density operator that depends on some parameter epsilon, you can write down its entropy in terms of the eigenvalues of that density operator lambda I as a summation lambda I log lambda I with a minus sign. Suppose it so happens that one of the eigenvalues is epsilon, a small number, and the second one is just 1 minus epsilon. Then for small epsilon, the derivative of the entropy with respect to epsilon is going to be logarithmic in epsilon. And this is what I refer to as a log singularity. It's quite general. It doesn't need to be this only 2 eigenvalue case. So long as there's some set of eigenvalues that increase linearly from 0 to leading order in epsilon, you'll get such singularities. And you can essentially use these singularities to develop methods to check the presence of coherent information and its non-additivity. And let me give you a simple example where this check is valuable. Think of what I call here an incomplete erasure channel, CG, with probability lambda sends the input perfectly, but with 1 minus lambda applies some noisy channel C1. Should the noisy channel C1 trace out the input to a pure state, then this will be an erasure channel with perfect transmission probability lambda. For this example, consider C1 to be a qubit amplitude damping channel with probability 1 minus P, so that when P is 0, everything gets damped, and this becomes the usual erasure channel with transmission probability lambda. Lots of colors. Focus on the cyan color at the P equal to 0 case, where this is the usual erasure channel. For such channels, it's well known that so long as the transmission probability is greater than a half, you have capacity and positive coherent information. Otherwise, you have 0 capacity, which is the quantity plotted on the y-axis, which is Q1 of this incomplete erasure channel, CG. Suppose you hold the belief that by increasing P slowly, the coherent information should somehow, the threshold at which it goes to 0 shift slightly to the left. So the cyan line which goes to 0 at lambda equal to 0.5 perhaps shifts to a little bit to the left as you increase P by a small amount. You run numerics and you see the graph, the one that I have plotted. And then you run numerics for a larger P, and then you get another line. You run numerics for a larger P for 0.45, you get another line, and P equal to 0.5, you get a straight line, and that's an algebraic result, and you are sort of convinced that your numerics are doing right, your intuition's okay, you report these results. Unfortunately, the numerics and the intuition are both incorrect. So the moment you make P positive, there are what I was calling logarithmic singularities, which give rise to the presence of coherent information for all values of lambda, the moment P becomes positive. To convince you of this fact, I have plotted in the inset the logarithm of the coherent information scaled by 100 for small values of lambda. So again, focus on the green line where P equal to 0.05. Notice what value log Q1 is taking. It's, look at minus 10 here. So it's going to be minus 10 at some value of lambda. So log Q1 is going to be a minus 1,000. Q1 is going to be exponential minus 1,000. Numerics, we're not going to find that value. Or the vanilla version of any numerics, we're not going to find that value. It's essentially these logarithmic singularities that are giving rise to the presence of this capacity. And this sort of happens quite generally, not just an amplitude damping channel. Think of any qubit channel with no capacity and a two-dimensional environment. You'll get similar curves and similar presence of capacity for all lambda. Okay. Well, this is just an example. What about more general cases? Well, you can get some general results by concentrating on these logarithmic singularities. And let me briefly give you a flavor of that. Essential idea is that, well, what does a quantum channel really do? It's this physical device into which you send a state, quantum state, and it rips it apart, sends part of it to the environment C and part of it to the output B. And suppose the output B has dimension dB, the environment is dimension dC. Just by looking at the dimensions of the input and the output in the environment and noticing if there is some pure state that goes to maximal rank, you can conclude whether, say, the output channel has positive coherent information. Um, well, this seems a bit esoteric, but you can apply it to solve this open problem, which was sitting around for a while. Essentially, if this output channel was a qubit channel, nobody knew when its environment has positive quantum capacity. The answer is given here. When the dimension is greater than 2, you have capacity. When the dimension is 2, the answer has been worked out. And when the dimension is 1, the answer is 0. Okay. Moving on from this general technique, which you can use in specific examples for checking positivity, you can also get some non-additivity example. The non-additivity example here is that I find a qubit amplitude damping channel which has no quantum capacity, and I use it in parallel with a simple qutrit channel to find this sort of different kind of non-additivity where two different channels used together have greater coherent information than the sum of the individual channels. However, one of the individual channels in this case has exactly 0 quantum capacity, which means a simple sort of 0 capacity channel can somehow boost rates for correcting errors or preserving entanglement, um, and so on. Okay, this finishes up the log singularity discussion. Now I want to give you a little bit of a conceptual surprise that has come about in the studies of non-additivity. The essential idea is that there is a belief that if you allow leakage of quantum information to a channel's environment, then this leakage is detrimental for its ability to preserve entanglement. The result is contrary to this belief. It says that the quantum capacity can be boosted by allowing leakage of quantum information to a channel's environment. Okay, what is this leakage? Let's go back to, again, the quantum channel picture. See, quantum channel is this device, as I said earlier, it takes in an input and it rips it apart in such a way that it sends two outputs, each of which is a valid quantum state. One goes to the B output, the other goes to trash, the C output. What do I mean by allowing leakage? Well, I expand the size of the input written by the green circle. The green circle on the right is larger than the green circle on the left. Then I expand the size of the trash and make that a larger space. And the expansion essentially is by connecting the input to the output with a perfect channel. And I don't do anything to the output. And this kind of modification is what I'm referring to a leakage, because the leakage sort of pipe becomes larger. And now I say, let's look at what happens to BL and compare it with the capacity of B. Essentially, the B channel under discussion has a qutrit input, and BL is, of course, larger. And let's go from top to bottom to understand what the result is. On the x-axis, there's a parameter lambda, which is a measure of noise in B and BL. This channel has only one parameter, lambda, and it measures noise. So on the top, I have this Q of B greater than 0 in the sky blue box. And there's an arrow which stops at a particular line, and that line is at lambda equal to lambda naught. So in that region, this channel has positive quantum capacity, and I know what it is. So somehow I've sort of bypassed all the additivity issues that I was referring to and constructed a channel for which I can actually compute these capacities. Then on the right side, to that line, there is this box where QB is 0 for greater values of lambda greater than lambda naught, the capacity is 0. Okay, now go one line below. I have done leakage, and so I've created this channel BL. Turns out I find that if you go from left to right, the quantum capacity of this B channel is strictly smaller than the quantum capacity of this BL channel. And it is not only strictly smaller in the region where the quantum capacity was positive for the B channel. It is also strictly smaller when the quantum capacity of the B channel was 0. And this region where Q of BL is positive, but QB is 0, lies between lambda naught and lambda 1, which is a half. It's a huge separation. Next, at lambda 1 equal to a half, the BL channel loses capacity completely and has 0 quantum capacity. Okay. So this is essentially the main result. How have I obtained this result? Well, here's some details. So I'll fill this in for the experts. Essential idea is that the dark line represents the capacity, which is the current information Q1. It goes to 0 at lambda naught. The dotted line represents the current information evaluated over 2 uses of the channel BL. And this is what is larger than Q1, and that Q1 was equal to the capacity of the B channel. Okay. With that, I will move on. Yes.
Yeah, I don't want to interrupt too much, but we've basically run out of time now. So if you could wrap up quickly.
And this is the wrap-up slide. The essential contribution of this talk is this theoretical tool, which is logarithmic singularities in von-Neumann entropy. The second contribution is a conceptual surprise, which is that allowing leakage of information can, in cases, boost the ability of the channel to send quantum information. And I want to end with a message, which is essentially that the study of these capacities and their non-additivity is a fundamental and fertile area for developing new theoretical and conceptual tools. And with that, I thank you for your attention and look forward to the questions.
Okay, so thanks a lot, Vikesh, for this very nice talk. So I'll open the floor to questions, and of course, since there's a bit of a delay between the live stream and us here, maybe I'll ask one myself, kill some time. So on page 12, I think it was page 12, where you were talking about the fundamentally new type of non-additivity. I'm not sure I got why it's like a fundamentally new type.
Yeah, I should have been more careful. It is a somewhat unexplored type of new non-additivity. Usually when people think of non-additivity, they make use of the same channel several times in parallel with itself. This is somewhat the most explored type of non-additivity. Using 2 different channels in parallel with each other is not as explored than that first case. That second case is explored in studies of superactivation. And there's a few papers on it. But studying when this happens for the current information, just the current information, is less so. So it's not a fundamentally new type. It's just if you view the definition of non-additivity that I had given earlier, which is in section 2 non-additivity. If you view the definition this way, then this is just non-additivity. There's nothing new. Right. But if you're more used to the definition where B prime and B are always the same, then this is perhaps slightly new. That's about it. It's not, yeah.
Yeah, I mean, it's to me, I mean, the case where you have 2 different channels was still quite a bit studied, right? Like if you take some channel with a 50% erasure channel, for example, right? Like this.
Yes,
is something
and
that
then
people have looked at.
People have looked at the 50% erasure with slightly more complicated channels. Let's put it that way.
Right. Yes. Yes.
Here, everything is somewhat simpler. Yeah. So yeah, yeah. Okay.
Okay.
Yeah.
So now we have a question from Omar Fauzi. And he's asking you to repeat how non-additivity is linked to log-singularities.
Right. I never said anything about it. The way the link works is as follows. A singularity can occur in the entropy of a joint density operator where the joint density operator is over the input of two quantum channels, rho A1 and rho A2. Suppose the singularities of the type where rho A1 and rho A2 individually maximize the coherent information of the individual channels. And it has the flavor that it increases the entropy at the output of the channel. Then you would be increasing the coherent information starting from a point where the coherent information was the coherent information Q1 of the first channel plus the coherent information of Q1 of the second channel. And the singularity will give you an uptick in the output entropy, but not in the environment. And this will give you a sort of non-additive result in that the coherent information of the joint channel would be larger than the sum. And is there something simpler I could say? The cleanest way of expressing this in the shortest number of words is in this archive reference.
Sounds good. I think that's a good place to stop, since now we have to go to the next speaker.
Okay.
So thank you again, Vikesh, for this very nice talk.